This is a working model showing the effect of changing the mass moment of inertia about the rotating system. So according to the angular momentum conservation, initial and final angular momenta remain unchanged if there's no external moment acting upon the system. So what do we have here? We have a relatively small mass rectangular body, and then there are two slides, one per each disc. The discs, so if the rectangle is only 0.1 kilogram, the discs are 50 kilogram each, and then there are actuators that change their length sinusoidally, same amount about the center, and all bodies have an initial angular velocity of 20 radians per second. Gravity has been removed. There is no gravity. It's like the system rotating in a horizontal plane. And I'm going to start a simulation, and you're looking at two graphs here. One is in blue is the angular velocity of the rod, which would be, of course, the angular velocity of the discs because they rotate with the rod. And the other one in the black line is the distance between the centers of the two rods. Of course, when the discs, which are much heavier, are closest to the axis of rotation, the total mass moment of inertia of the system is a minimum, and the angular velocity is a maximum. When at their farthest point, the angular or rather the mass moment of inertia of the assembly is a maximum, and the angular velocity is a minimum. Again, angular momentum about the axis of rotation, which is also the centroid because of the symmetry, it's moment of inertia times angular velocity. Now, if moment of inertia changes, then omega has to adjust in order for the angular momentum to remain constant. Okay, this is a simulation very similar to a figure skater who spins about in vertical axis, and by moving the arms away from the body slows down, and moving the arms close to the body, the speed is increased, rotational speed is increased of the skater. Okay, so this was it, and thank you for watching.